So yesterday we kind of just started off with a bit of revision about manifolds, and today I want to continue this sort of slightly more mathematical theme in terms of the sort of mathematical foundations of GR by talking about the Lie derivative. So David assures me he didn't do that with you. Is that right? Yeah. Okay. So this is essentially another way that we can take a derivative on a manifold without all the extra structure of a connection, a metric, or whatever. So the idea of the Lie derivative, again, it's in some sense making use of this notion of anti-symmetry. The exterior derivative and forms worked because they were completely anti-symmetric. So if you kind of got to the more pedestrian way of thinking about a vector in terms of the way it transforms under coordinate transformations, you saw that the piece by which a partial derivative was not covariant was symmetric. So if you anti-symmetrized, you got rid of that. So that was how the exterior derivative worked. So the Lie derivative's going to be sort of... It's a bit different, but it's got the same spirit. In the case of the Lie derivative, what we're going to do is we're going to use a vector field to kind of link together different points. But what I want to do first is just to pick up on this theme of anti-symmetry and to just look at something which is, in some sense, a derivative. So remember, we said that vectors were operators. They took an element of C infinity of m and kind of mapped it to another element, at least locally at a point, which was the derivative of the function along a curve. So it's an operator, but we have this sort of geometric visualization of it as a sort of direction and magnitude. So f goes to df dt. So let's consider this anti-symmetric combination of two vectors. So one vector acts on a function to give the derivative. So that's also, if you like, in some sense, another function. So we could act on it by another vector. So let's consider this. We see that it's also anti-symmetric. It's like a commutator of u and v. So if you remember, we also wrote in components So if I write down each of those operators just with respect to their components in a coordinate basis, this is what I'd get. Now, so this d by dx mu is acting on both the v as well as the derivative of f. Now, because of the symmetry of partial derivatives and the anti-symmetry of the u and v here, the term of this, which is a second derivative of f, cancels out. So we get all we get are partial derivatives of each of the vectors respectively. So I'm not sure whether you did this notation, but a comma just means a partial derivative. So here you see that this is now, if you look at this, these are the components of a new vector. So we call this vector uv, and it is the Lie bracket or the commutator. So even though we don't necessarily have a differentiation, here we're starting to sort of build up a bit more structure. So we know we can do forms by anti-symmetrizing covectors, but we can start to build a bit more structure on vectors. And in some sense, this is a derivative. So the sense of which, of course, we're going to explore. So if you think about kind of what's happening, here are our two curves that are associated to u and v, and when we take the tangent vector, we kind of take a derivative along the v curve. And so what we're sort of doing here is looking at how that changes along u, this first term, the uv. And then the vu piece is just the same swapped. So here, if you remember, a derivative, just see how I wrote it notationally. Just if I kind of write it in abstract, a derivative is sort of the difference between an object at two neighboring values of your parameter t, and you take the limit as that difference goes to 0 of the difference in your object q divided by this small increment delta t. So as you learned in the first GR course, the problem that you have on a manifold is that if you're comparing two neighboring points, p and p plus delta p, these are different tangent spaces. So you have to have a way of comparing things in different tangent spaces. So what you learned was the connection, which connected the different tangent spaces together, that we'll also just be quickly reviewing. But here, what we're doing is we're going along like this U curve. So this is what, in some sense, we're doing. And we're using the U curve to take the derivative. So that's the notion. Here I've just done it in a rather formal sense of looking at something that's anti-symmetric. But now I want to sort of pick up on this idea of going along U curves and taking differences and using U to transport quantities from one point to another. So I'm posing it as a question at the moment because we have to make that obviously more precise, but that's basically what underlies the Lie derivative. We use a vector field to link together tangent spaces, but it's very specific because it's linking them together along that curve U. So in order to pick this apart, we need to just sort of familiarize ourselves with a few things about maps, because what we're kind of doing here is we're taking a tangent space and sort of mapping it along. We're sort of nudging it along that curve. So we just want to see how we do that formally and what it tells us about how that Q transforms. So let's suppose we've got two manifolds, M and N. And in general, we don't need to assume that they're the same dimensionality. But we have a map from one manifold into the other. Now, today, we're going to assume they have the same dimensionality because we're mapping the manifold into itself. But we'll see examples probably next week where we genuinely map manifolds of different dimensions. So, for example, you could think of this as a submanifold. You map a two-dimensional surface into three dimensions. So that's an example which is has physical meaning where you're not mapping between manifolds of the same dimension. So let's say this is an x coordinate chart, this is a y coordinate chart, and underneath, corresponding to this map between the manifolds, we can kind of go down into the local charts and have a corresponding map between r to the m and r to the n. So this is where we sort of poach our differentiability from. We look at what happens in the corresponding charts. That's always what we're doing with manifolds. So that's a general map, but if the dimensionalities are equal, and our function is one-to-one onto C infinity, etc., you know, all the usual things that we want it to be, then we say that this F is a diffeomorphism and we regard M and N as being the same. So, in the back of our minds, we are thinking of a diffeomorphism. But again, in general, if we refer to this picture, once we have a map between M and N, we can also construct maps between the tangent space of a point in M and the tangent space of a point of its image in N. And we can also take the cotangent space in N and relate it to the tangent space in M. So this is, again, because we have this notion of vectors as differential operators, so we're kind of going forward and down sort of thing, or back and down in each case. So just to say what these are. So our push forward is sort of pushes our tangent spaces forward. And so we have a picture of, let's say, a curve here, gamma t in M and gamma s in N. Let's put them the other way around, t there, since it's d by dt, and s. So all we do is we know that our tangent vector in M is a tangent to a curve. We have a curve in M. It maps to a curve in N under the function f. We take the tangent vector of that curve, and that gives us the relation between a vector here and a vector there. So that's how we push forward. And correspondingly, because covectors are maps from vectors to the reals, that means that we can pull back the cotangent space of n onto the cotangent space of m. Because if we have a map from a vector in Tp of n to the reals, then we kind of know how to map our sort of pre-image what did I call it? I called it T there. So our pullback here of an omega that is in TQ star of n acting, so the pullback of that one form acting on the vector t is defined as the one form omega acting on the push forward of t, which is s. Okay. So that's how we define these maps. Now, again, if we have F as a diffeomorphism when M and N are the same, we can both push forward and pull back. So we can do both. We can push forward a cotangent space and pull back a vector space because the two manifolds have the same dimensionality and our F, if it's a diffeomorphism, goes both ways. So we basically got a complete sort of equivalence of the various vector spaces. So what does that have to do with this vector field U? So just to draw a picture, so let's suppose we have this vector field U, and we have this set of curves, and these are called integral curves, and that just means that everywhere on the curve U is a tangent vector. So how does this define a diffeomorphism? Well, remember a diffeomorphism, if it's between two manifolds, we regard the manifold as the same. So what we can do is we can take these integral curves and imagine just sliding a little distance, delta t, along each curve. So that is kind of you can think of it as sort of shifting the points or relabeling the points. You've got a sort of active and passive view of that. But in any case, it's kind of just like deforming your manifold a bit. You're just shunting it a little bit along these integral curves. So although here it sort of all looks uniform, you could imagine that t runs at different rates along the curve, so it might bunch up in some places and stretch out in others. But it's essentially just the same manifold. You're just kind of doing this little nudge on it. So this is you could think of it as giving a new chart or just shifting the points of the manifold around a little bit, just playing with it. So that now gives us a way of comparing quantities at nearby points, because we've got this pull back and push forward. So just notionally, if this is our Q at a point P, this would be our Q at P plus delta P. And now we know how to push forward that Q to the point P plus delta P. So this is the idea of what we do with the Lie derivative. We push forward or pull back, whichever's relevant, depending on what Q is, from P to P plus delta P. We compare that to the actual value of that geometric field at that point, and then divide by delta t, take the limit as delta t goes to 0. So that's what we do when we take derivatives. So let's look at what happens for a vector field. So here, we're going to look at V at t plus delta t. So here, that's going to be the value of V at x naught plus delta t u. So that's what we're trying to evaluate. So if I put that in a coordinate basis, then the components of V at a neighbouring point are just going to be V at the initial point plus its derivative along that curve. Meanwhile, we want to compare that to the pushed forward version of V. And so to push it forward, we're simply doing this transformation. Where is it? So we want to kind of look at how this differential operator changes, and that just changes by the Jacobian of this transformation. Hoping I've got all the indices tallying up here. And so we subtract these two. You see that the leading order term is the same. It's v d by dx, which is the same over here. And so our derivative So when I subtract these two pieces, I find that what I get is right there in the middle at the bottom of the first board. So I've got the same expression in terms of derivatives. So you start off with the derivative of v along u, you subtract the derivative of u along v, And so this is just our Lie bracket. But we've come to it from a very different point of view. And the way that we've accessed it here by, instead of just doing that commutator, which is only going to work for vectors, the way we've accessed it here is going to work for vectors, covectors, tensors, etc. So this method gives the general Lie derivative. So if we apply it to a one form, then we see that the sort of minus here, in terms of the components, becomes a plus. And essentially, if I look and write it for a two, not a two form, a covariant rank 2 tensor. So let's look, say, for example, the metric. All that you do, it's easier to sort of write this out in component form, but what your first term is always the derivative of the geometric quantity, partial derivative, along the vector u. And then for every single index, you sort of use either the covector or vector rule. So in this case, if it's a covector, you replace, you sum over the index with u and take that, sort of turn the free index into a partial derivative, and you do that for every index. If it's the contravariant index, then the free index is kind of on the vector, on the u vector. So that is the sort of general expression for this Lie derivative. So what's it good for? Well, the first thing that we can think about is, what does it mean? What's its geometrical significance? So I'm going to go to the Lie bracket. There's two sort of features in which we think of this and think about what it means geometrically. So the first, if we go back to thinking about our u and v, let's consider what happens if we go a little distance, small distance s, along v, and then a small distance t along u, compared to a small distance t along u, and then a small distance s along v. Then there's no guarantee, if you go along integral curves of vector fields, that it's going to be the same, going along u then v versus v then u. And if we look at that commutator that we saw right at the beginning, that is kind of saying, well, I do v first then u, and I compare it to u first then v. And if that's non-zero, the Lie bracket is non-zero. So I might expect that this discrepancy here between the points B and D should be somehow proportional to this Lie bracket. So I just expect that because on the way we defined the Lie bracket is like a commutator of vectors. So it is like saying do one first, then the other, and compare it to the reverse process. So let's actually see that in action. So again, we have to expand things out. So in this case, if I just sort of look, it's a bit crude, but if I look at that, imagine both S and T are of order epsilon, then I expect the difference between B and D to be order epsilon squared. So just that's a sort of, just a sort of pictorial kind of very dodgy argument, but it's motivating why, when I write things down, I'm going to expand them to order S squared, T squared, or ST. So if I look at the coordinates of the position A, the point A that I've written down, then I have to expand to order S squared, and this is what I get. I also need to know how to just sort of recall how to transport my vectors from one point to the other. So when I put a subscript on my vectors, it's just emphasizing that they're kind of living in the tangent space at the point 0. So the strategy is going to be, oh, I didn't think that was what I pressed, but never mind. Can you read that, or are the lights on it? Is it all right? It's okay? All right. Maybe it's just me that's got the lights on it then. So the strategy is going to be, we're going to use those sort of general rules for expanding both the coordinates and the vector fields to find the coordinates of the point D, the coordinates of the point B, and then we're going to subtract those two. Now, obviously, if this were on the manifold, it would be a bit dodgy, taking a difference in, in 2 points, but we're using the notion that we've come down into a chart, and to within order S squared or T squared, this is a legitimate thing to do. So let's first find the coordinates of the point D. So D comes from C, and so I use that expression that I wrote down there. And the first, I'm coming to D from C, so the first 2 pieces I have to annotate as coming from C. But because the last term is already multiplied by S squared, I can reduce everything down to the point O. And then XC is, of course, X0. Sorry. So that's my XC. So I need to transport my vector from C back to 0. So I've just used the second expression there. which of course has u's and v's and s's and t's swapped. So that's my expression for x mu at d. To find the expression of the coordinates of B, all I do is swap the ordering of u and v. So I swap s and t and u and v. So if I use colours here, this term here, obviously, if I then subtract off, this term is the same in both. I've also got a t u naught here with an SV. So these two terms are invariant under the swapping of u and v and s and t. Similarly, these two terms here are also symmetric under that swap. So the only term that's left is this one here. So as advertised, when I kind of go through all the algebra, I find that the difference in the coordinates of the points D and B is indeed the commutator. So that means that the Lie derivative tells us something about coordinate when vector fields are tangent to coordinate lines. So if a vector field were tangent to a coordinate line, then that would mean that, say, u was d by du, where u was a coordinate, and v would be d by dv, where v is a coordinate. And since partial differentiation commutes, the commutator of u and v would therefore have to vanish. So this means that if u and v are these coordinate, so the integral curves of u and v are coordinate lines, then their commutator has to vanish, because the whole point about a chart is it gives you a unique labeling of each point in terms of coordinates. So another way the Lie derivative is important or useful in GR is that it relates to symmetries and symmetries of a metric. So I just want to introduce a definition, which I don't know, come across, but a killing vector killing vector is defined as one along which the Lie derivative of the metric vanishes. And it represents a symmetry of the space-time. So here you can see that if we write it in the sort of longhand way of what it means in terms of components, it doesn't actually look that helpful. But what you'll find when we do the covariant derivative is it's actually entirely equivalent to the symmetric part of the covariant derivative vanishing. So this actually gives us some important information about space-times. And at least in abstract, if you know your space-time has certain killing vectors, that allows you to choose coordinates to simplify the metric considerably. So you already know that the metric is a symmetric two-form, which means it has, strictly speaking, 10 components, possibly, 10 independent components. But if your metric has symmetries, you can use these sort of relations from these killing vectors to kind of reduce the number of degrees of freedom in your metric. So let's just look at, let's say, a two-dimensional example. Which is the metric on a unit 2 sphere. So here we see that if we do, I mean, although this is obviously there's a whole SO3 set of symmetries of this manifold, the easiest one to notice is that if we rotate around the axis of the sphere, the metric is invariant. So the metric does not depend on phi. So if we define our killing vector, or a killing vector, as d by d phi, in components our k phi is 1 in a coordinate basis, then we look at our expression for the Lie derivative, because the components of k are just constant, it's just either 1 or 0. When you take a derivative of k, these two terms vanish. And so here you see that if this is a phi, then this is just partial derivative of g with respect to phi, which vanishes. And so here, the fact the metric is independent of phi is sort of completely equivalent to saying its Lie derivative vanishes. So this is a killing vector, d by d phi. Now, in fact, here, just as an aside, we also have two more killing vectors. So hopefully I've got the signs right and the orderings here. But these two killing vectors, if I label them K1 and K2, these correspond to other SO3 rotations. So obviously, if you have a two-sphere, it's not just symmetric under rotations around the axis. You can sort of rotate it in sort of different ways. You've got three, different possible orientations. So these correspond to these different killing vectors. And together, these three killing vectors obey an SO3 algebra. So that means that the algebra of the killing vectors is kind of reflecting the underlying symmetries of that particular space, that geometry. And so I leave it as an exercise to check that I've got the signs right. I know the form is roughly right, but I may have messed up with the sign. So in preparation for discussing connections more tomorrow, I just want to kind of wrap up today by, again, coming back to this question of bases, because as we move forward, we're going to be using a notion of this Vierbein or Vielbein or arbitrary bein or whatever. So our Lie derivative works because it has a geometric way of connecting tangent spaces. It's tied to the vector field, the underlying u or k, whatever you're taking the Lie derivative with respect to, but it nonetheless is working because it gives you a prescription for connecting vector spaces. So we know that the connection is a structure that we can add to a manifold So it's actually a structure on the tangent bundle which is linking together tangent spaces at nearby points. So it's a way of saying, if I have a basis at one point, this is how it maps into a basis at a nearby point. So this is the way in which we're going to introduce the connection. So rather than kind of thinking of grad in terms of actually being a derivative or the Christoffel symbols, think of it more as taking, some little basis at one point and shifting it to a basis at a nearby point. So if we just sort of think, just as, again, David said that often, you know, this language of basis and basis vectors can sometimes sort of take a bit of getting used to. I thought I would just add a bit here, talking a bit more about vectors and bases. So let's just think of R squared, flat R squared, with two different charts. We've got standard Cartesians and we have cylindrical polars. So if our Cartesian basis would just be d by dx and d by dy. This is both coordinate and orthonormal. And I think I said this when I was talking about bases previously. But we've got here, if we look at the right-hand side, d by dr, which is x on r er plus y on r, x on r ex. So these are my coordinate bases in polars. So the mod of ER, the norm of ER is 1, but the norm of d by d theta, or this vector here, is r. So this is not orthonormal. It's orthogonal, but not orthonormal. So I've sort of said that what we're going to sort of find as we look tomorrow at Cartan formalism, we're going to find that orthonormal bases are quite useful. So here our orthonormal basis, ER, is d by dr, and E theta, if I put a hat on it just to emphasize that it's an orthonormal basis, that would be 1 over r d by d theta to kind of cancel off that r factor there. So this is our orthonormal basis, and we could write it equivalently in matrix format. So here we have our orthonormal, here we have our coordinate basis, and here we have what relates the two, which is a matrix of components. So here, so you'll be seeing this a lot in the next couple of days, this is what is giving us a translation between our coordinate basis and our orthonormal basis. In some sense, it's a square root of the metric, because you can sort of see that if you have, I suppose it's the square root of the inverse metric. but you have eta A hat B hat so this is kind of giving you a relation between, because it's orthonormal, it's telling you something about distances. And so what we will, if you notice, if you draw your coordinate system, so that's theta, this is r, y, and x, your orthonormal basis always has an ER pointing outwards. But if I go to a different point here, let me go a bit further out there so it's more obvious. My ER and E theta have rotated. So although the xy coordinate basis is the same throughout the plane, as I move throughout the plane, my ER and E theta basis changes. So you will have seen all this probably when you first sort of did vectors as undergraduates, and you would have seen this sort of orthonormal basis in terms of polars. But actually, what you were doing was kind of practicing differential geometry, but on a flat manifold. So what you see here is little shifts in ER are expressible in terms of E theta delta theta. So if you are linking together tangent spaces, if you go radially outwards, your ER and E theta do not change. If you go around the circle, however, ER changes a little bit in the theta direction, and E theta changes a little bit in the R direction. So these are giving you a connection between the different tangent spaces. So these are sort of giving you theta R components and theta R theta components as being non-zero. So we'll come back to that tomorrow, defining the connection in a general way in terms of how it acts on basis vectors, and then finding a general way of computing it via Cartan. But keeping this in mind might help in terms of the notation and what it means in an underlying sense. All the connections doing for you is telling you how to relate bases from one point to another. And although this space-time is flat, it doesn't necessarily have a zero connection. And indeed, if you're in polar coordinates, it doesn't. So it's just kind of useful to keep that in mind when you're sort of dealing with this much more abstract formalism potentially on a curved manifold. Okay.